In section 3.6, we will learn about derivatives of logarithmic functions, including a new technique for taking derivatives of very complicated functions, which involve lots of products, quotients, or powers. Let's start by setting the rule for computing the derivative of a general logarithmic function. We will prove this rule in class, but for the purposes of the video, we will just state the main result. If y equals log base a of x, then the derivative y prime equals 1 divided by x times the natural log of a. For example, if y equals log base 3 of x, then y prime equals 1 divided by x times the natural log of 3. What about a slightly more complicated function? What if y equals log base a of a function f of x? Here, we can use the chain rule. Following our basic rule, we see that y prime will equal 1 divided by the function times the natural log of a, and then we simply multiply by the derivative of that inside function, f prime. Note we can also certainly write this as f prime divided by f of x times the natural log of a. Let's do an example. Suppose y is log base 3 of sine of x. Then following the above rule, y prime equals 1 divided by the function sine of x times the natural log of 3, and then times the derivative of sine of x, which is cosine of x. We can clean this up and simply write it as cosine of x divided by sine of x times the natural log of 3. Certainly, the most important logarithmic function is the natural log. Here, again, is our general formula. Let's see what our rule becomes in the special case of the natural log. If the base a equals e, then our logarithmic function is the natural log of f of x. And so, y prime will equal f prime divided by f times the natural log of e. Recall that the natural log of e is just 1, and so we have y prime equals f prime divided by f. So our rule states that the derivative of the natural log of a function is the derivative of that function divided by the function, f prime divided by f. For example, if y equals the natural log of 3x to the 4th, then y prime equals 12x cubed divided by 3x to the 4th. Notice this is just the derivative of the inside function divided by the inside function. This simplifies, of course, to 4 divided by x. Suppose we want the derivative of the natural log of tangent of x. According to our rule, this derivative will equal secant squared divided by tangent, the derivative of the inside divided by the inside. Here's a more complicated example. Suppose we want the derivative of the natural log of x plus 2 divided by x minus 4 to the 5th power. Now, in order to compute the derivative of the inside, the f prime piece, we will need the quotient rule. So we have the bottom, x minus 4 to the 5th, times the derivative of the top, which is 1, minus the top, x plus 2, times the derivative of the bottom, which is 5 times x minus 4 to the 4th power, times the derivative of that inside function, which is just 1, all divided by the bottom squared, which is x minus 4 to the 10th. All of this is our f prime of x. And then we divide by f of x, which is x plus 2, divided by x minus 4 to the 5th. Whew. This is a pretty complicated example, and the simplification here would also take some work. Let's do this example another way, first using log rules to simplify our function. To simplify, recall that logs can pull apart quotients using subtraction. So the natural log of x plus 2 divided by x minus 4 to the 5th equals the natural log of x plus 2 minus the natural log of x minus 4 to the 5th. We can go even further by moving the exponent 5 down in front of the natural log. this becomes the natural log of x plus 2 minus 5 times the natural log of x minus 4. And so instead of taking the derivative of our original complicated function, we can take the derivative of this version instead, which consists of simple pieces. Using our derivative rules, the derivative here is 1 divided by x plus 2 minus 5 times 1 divided by x minus 4. Notice that in this example, we simplified our function using log rules before taking the derivative. Our simplification broke the original function into simple pieces, each of whose derivative was quick and easy. We can actually do something similar for functions that aren't logarithms. Our big idea here is that for functions involving lots of products, quotients, or powers, taking derivatives can be simplified using a method called logarithmic differentiation. Let's see this method in action in an example. Here, we want to find the derivative of sine of x to the 8th divided by 3x plus 4 to the 6th. We could certainly dive in with the quotient rule, but let's use our new method instead. We want to be able to use log rules to simplify, but this function doesn't contain a log. Therefore, we will introduce one. Just remember that whatever we do to one side of an equation, we must do to the other. So our first step is to take the natural log of both sides of our equation and then simplify using log rules. So we have the natural log of y equals the natural log of sine of x to the 8th divided by 3x plus 4 to the 6th. We can pull the quotient apart into subtraction and then move the powers down front. So we have the natural log of y equals 8 times the natural log of sine of x minus 6 times the natural log of 3x plus 4. Keep in mind that we haven't taken a derivative yet. We've only changed and then simplified the original function. Step 2 is to differentiate implicitly. As a reminder, here's our rule for the derivative of the natural log of a function. We do the derivative f prime divided by f. Since y is a function of x, when we take the derivative of the natural log of y, we get y prime divided by y. Then, continuing to follow our rule, we have 8 times the cosine of x divided by sine of x minus 6 times 3 divided by 3x plus 4. We can simplify the right-hand side to 8 times the cotangent of x minus 18 divided by 3x plus 4. Our third and final step is to solve for y prime and substitute for y. We solve for y prime by multiplying y to the other side of the equation. And then we plug in that y equals sine of x to the 8th power divided by 3x plus 4 to the 6th. Awesome, so we found our derivative. Let's review our 3 steps. First, we took the natural log of both sides and simplified using log rules. This broke our complicated function into simple pieces. Then, we differentiated implicitly. Remember that since y is a function of x, the derivative of the natural log of y is y prime divided by y. Finally, we solved for y prime and substituted for y. Here are the 3 steps one more time. Take the natural log of both sides and simplify using log rules. Differentiate implicitly, solve for y prime, and substitute for y. Let's do one more example. Let's find the derivative of x to the 4th times tangent of x cubed using logarithmic differentiation. First, we take the natural log of both sides and simplify using log rules. Here is the natural log of both sides. We pull the product apart into a sum and move the powers down front. Step 2, we differentiate implicitly. The derivative of the natural log of y is y prime divided by y. On the right-hand side, we get 4 times 1 divided by x plus 3 times secant squared divided by tangent of x. We can clean this up slightly. Finally, we solve for y prime and substitute for y. To solve for y prime, we simply multiply y to the other side of the equation, and then substitute that y is equal to x to the fourth times tangent of x cubed. So our final derivative, y prime, is x to the fourth times tangent of x cubed, all times 4 divided by x plus 3 secant squared divided by tangent. It's a fair question to ask whether in this example our new technique was necessary. Why not just use the product rule? For this example, you're absolutely right. The product rule would have worked beautifully. But the goal was to introduce a new technique, and simple examples are the best introduction. So come to class for the real answer. We will do much more complicated examples where our new technique of logarithmic differentiation will be required. I look forward to seeing you there.